All right, so welcome again to Research TTIC. Today we have Ohad Trabelsi, one of our research assistant professors here, talking about his work on ruling out certain kinds of lower bounds for all pairs max flows. So please take it away.
This is a rather recent manuscript I'm going to talk about. I'm going to focus on the following problem. So it's called the all pairs maximum flow. And in this problem, we're given a graph. And we need to output for every pair of nodes the maximum flow between them. Many of you probably heard about the all pairs shortest path problem, APSP. So that's essentially the same, just instead of the shortest path, we look for the maximum flow. Now, this problem it turns out that it's quite easy or can be solved quite fast in undirected graphs with edge capacities. A recent line of work, we and others managed to show that in order to solve this problem, it is enough to apply essentially roughly one time maximum flow between one pair of nodes. Following that success, we ask the following question: how fast can we solve the all pairs maximum flow problem in other settings? Maybe the edges, maybe the capacities are on the nodes, and maybe the graph is directed. So many other settings. And in particular, we want to know whether we can, when we can surpass the naive algorithm, which is simply to apply maximum flow between every pair of nodes, which is m squared times m. Because maximum flow was recently shown to be solved in linear time. Okay, here's a little sketch of the settings and the known relationships. So, undirected, edge capacitated setting, that's the easiest, can be solved very fast. Directed graphs with edge capacities is the most difficult one. And there are some other settings in between. But we do know that every setting that is not undirected graph with edge capacities, it's unlikely that it can be solved very fast. And I'll expand on it in a moment. Okay, so what is known? So as far as arbitrary capacities, the naive algorithm is the fastest known. Okay? And if the capacities are unit, so either unit node capacities or edge capacities, then some faster algorithms exist.
So you're always looking at the exact values, right? The exact
values. Yeah. In this lecture, yes. Yeah. So
is exponent of matrix multiplication.
Yeah. Omega is the fast multiplication exponent. Yes, it's 2.3 currently something, and I'm going to assume that it's 2 essentially. So unit capacities, some faster algorithms are known, but still for dense graph, it's not faster than the naive algorithm. It's just n to the 4th. Now, what is known as far as hardness results? So first, as far as the size of the data structures, we know that no succinct data structure exists for all pairs max flow in all of the hard variants. So as opposed to the setting that I said that it's easy, the edge capacitated undirected graphs, where there is what is called Gomery-Hu tree, which is a very succinct data structure of size O of n. In all of the other settings, the hard variants, it is known that there isn't a very succinct data structure. Now, as far as algorithms, we know that all of the hard variants, so again, all of those variants that are not the most easy variant, admit an n to the fourth combinatorial conditional lower bound, which means a conditional lower bound against combinatorial algorithms. A combinatorial algorithm is something that is not well defined in the community, but essentially an algorithm that doesn't use fast matrix multiplication techniques. And that lower bound assumes the four-click conjecture. The time required to find whether a graph has a four-click is n to the fourth without fast matrix multiplication techniques. Okay. Now, as far as any algorithm, not necessarily those combinatorial algorithms, we know that all hard variants admit an n to the 3 conditional lower bound, assuming the SETH, the strong exponential time hypothesis. It essentially says that SAT requires 2 to the n time. Solving SAT requires 2 to the n time. Okay. So the main question here is, can we show n to the fourth conditional lower bound for any algorithm, not just combinatorial algorithms, for all pairs max flow under SETH, under SETH? If we succeed in that, it would mean that the naive algorithm is the best that we can hope for. And the new result is that it is unlikely for most of the hard variants. And by unlikely, I mean, if we could, then another hardness assumption called SETH would break. I'll explain it soon. The proof method is by finding a fast non-deterministic algorithm and using an existing framework. And now let me parse all of the definitions. So first, what do I mean by non-deterministic algorithm? So that's an algorithm that can make guesses or non-deterministic choices, and then eventually produces either a correct output or don't know. And we also want that there's always, for every input, there is a correct guess. Okay? So this is a straightforward definition. And SETH is an extension of SETH, of the strong exponential time hypothesis. What it says is that SETH holds against non-deterministic algorithms as well. So if we want to solve SAT non-deterministically, there is still nothing better than 2 to the n, specifically for the disproving SAT. So for showing that SAT formula is unsatisfiable, we would still need to essentially go through all of the assignments. Okay, so what is the framework that we're going to use? So essentially, if problem A can be solved in non-deterministic time quite fast, let's say, and also we know that there is a reduction from SAT to the problem, fine-grained reduction, then what it says is that the savings on problem A would transfer to SAT. And in that way, we are able to say that such a reduction is unlikely. This is essentially the method. Because then we would, given a SAT formula, we would apply the reduction, and then apply the fast non-deterministic algorithm, and then solve SAT faster non-deterministically. Another way to see it. So let's say there is a gap in the fastest algorithm and the best conditional lower bound that we have for a problem. And we're stuck on both. Okay? We try to find a better algorithm and better conditional, we just can't do it. One way to move forward is to design a fast non-deterministic algorithm. And then the conclusion would be that the conditional lower bound assuming SETH is unlikely. So it's essentially a lower bound on the lower bound. It's one way to kind of tell ourselves which angle is maybe worth our time. Yeah, maybe we should kind of spend time on the algorithm side. Okay. So now this is this is a new framework in this paper for finding faster non-deterministic algorithm. What it says is that if we have an algorithm with some structure, so the structure is that this algorithm is Las Vegas making some like Q amount of maximum flow calls between single pairs, and spend some additional time, t. And let's say that in addition to that, we have a flow volume upper bound. What is the flow volume? Is an amount of edges required to represent the flow. Okay, so for example, if we're talking about graphs with unit and node capacities, we know that O of n is enough to represent the flow because the flow paths are disjoint. Okay, so given an algorithm and a flow volume upper bound for the corresponding setting, then we have a non-deterministic algorithm with running time Q times something, the volume plus n, plus the additional time. Now, why this is meaningful? Because in the standard world, normal algorithms, not non-deterministic algorithms, that would take Q times m, the time to run a maximum flow routine, plus t. So here, we improve it a little bit. It's Q times the volume plus n plus t.
And can you define what is flow volume?
Yeah, I just say. So again, it's so let's say you have a pair of nodes, S and T, and then there is the maximum flow between them, right? So you have an actual flow there. Now the question is, in this setting, so whatever the directions, the node capacities versus edge capacities, is there a bound on the number of edges that you need to represent the flow? So in general, you can always do with just n squared, the amount of edges in the graph. But sometimes maybe you don't need all of that. So you can do it. Maybe there is always a bound that is enough to represent the flow.
And flow between all pairs, right?
Between just a single pair.
Oh,
yeah.
So volume of F, and here you're assuming that this bound is just for a single pair?
Yeah. So in some settings, maybe there is a bound. I will talk about it more, but maybe in some settings there is a bound that is non-trivial. So the trivial bound would be to use maybe all of the edges or all of the edges. So maybe in some settings you can do something better. So for example, if it's unit node capacities, we know that the paths are disjoint, are node disjoint. So the total size required to represent the flow is O of n.
Okay.
Right? Okay. Maybe in some other settings there is also some. Yeah.
So algorithms on these slides they are for a general instance of satisfiability, or what is the problem?
No, so this is for all pairs maximum flow. Satisfiability is relevant for SETH. This is the hardness assumption that is in the background. Yeah. So we show.
So you want to solve all pairs, and you allow Oracle access to every individual pair. What does it mean? MF calls.
Yeah. So it's maybe we should go back to the definition of non-deterministic algorithm.
Yeah.
So this is an algorithm that can make non-deterministic guesses, and we want that algorithm eventually to produce either a correct output, so given the graph, like a data structure for the all pairs maximum flow, or don't know. And also we want that there's always a right way to do it. So for every input, there is a correct guess. So the algorithm can make the correct guess. So what I'm trying to do is to find a way to design fast non-deterministic algorithm for all pairs maximum flow. Why is that good? Because then we would be able to apply this method. So if I show that there is a fast non-deterministic algorithm for the problem, then it essentially means that there is no good reduction. Because if there was, we would be able to solve SAT non-deterministically fast. Any more questions? Okay. So not just given that framework, let me show you some of the consequences. So first, for directed graphs, even with arbitrary node capacities, that implies a non-deterministic algorithm with running time n-cubed. And that is matching a known lower bound, a known conditional lower bound even for undirected sparse graphs. So what it means is that this conditional lower bound cannot be improved. And how it is achieved by using the naive algorithm, so n squared times the time of maximum flow, and then also using a new volume upper bound for this setting. So this is another new result here that so for the setting of even directed graphs with arbitrary node capacities, it is always enough to use O of n to represent the flow. Right? Even if the given graph has n squared edges, you always don't need all of that.
And the capacities are arbitrary. is
Yes,
what you said.
arbitrary capacities, yeah. Even for arbitrary capacities. For unit capacities, that's immediately, but even if the capacities are, let's say, arbitrary. Okay, so right, so Q in that case would be n squared, the volume would be n, and then it's just n to the 3. That's how we apply. Now the second setting that is of interest here is undirected graphs with unit node capacities. For this setting, this framework can get us to O of Mn, a non-deterministic algorithm with running time Mn. And the way that this is achieved is by a new Las Vegas algorithm, so standard algorithm with the running time of M applications of maximum flow. That improves some existing algorithm. I'll talk about it soon, independently. And also using the natural volume upper bound. So for this case, the volume is always upper bounded by O of n for the unit node capacity. And that implies the Mn non-deterministic algorithm. Now, as far as this independent improvement, in the standard realm of algorithms, maximum flow can be solved in O of m time or near linear time, m to the 1 plus little O of 1. So that means an algorithm that our Las Vegas algorithm has running time m squared. So that is the red line here, which improves a recent algorithm for the same problem, and also makes it Las Vegas, and it was a Monte Carlo. Yeah, and we have the this is the non-deterministic running time, and that is the conditional low bound. So essentially, what it means is that conditional low bound cannot get better than that. The yellow line cannot be better. And the last setting that I want to tell you about is directed graphs with unit edge capacities. So in this case, the non-deterministic algorithm has running time something that is always less than n to the 4th. So again, what it means is that a conditional low bound showing n to the 4th is unlikely. And that is achieved by, again, the naive algorithm and a volume upper bound that was known in a different context. So Karger and Levin showed that in this setting, the volume is always at most n times the value of the flow, square root of the value of the flow. Okay. So now let me tell you a little bit about the techniques. So first, I want to start with the framework, and then the volume upper bound and maybe the randomized algorithm if we have time. Okay, so this is the slide of the framework. So what it says is that we're given an algorithm and a flow volume upper bound, and then there is a non-deterministic algorithm. How do we show that? So the high-level idea is to first guess the set of node pairs that the algorithm will call. Okay? And then also guess the maximum flow for them. And then just to run the assumed algorithm, the Las Vegas algorithm, or the deterministic. And then whenever it is supposed to make a max flow call, then we go to the available information, what we guessed, and then we just say, okay, here is the result. This is how we get the speedup. Okay, now, so now let me focus on number one here. This is the tricky part. How are we going to do it? So we guessed set of the set Q of node pairs for which the max flow are going to be called, and also the corresponding values. So there's a value for every pair. And then we want to guess the cuts and the flows separately for the pairs, and then make sure that the values are what we guess for them, and also make sure that they're feasible. So we have different cuts for different pairs and flows. We want to make sure that they're feasible and that the values are what we guessed. If the values are what we guessed, the values are the same, then by the max flow min cut theorem, we know that they are optimal. Okay? So let's focus on the specific setting of undirected graphs with unit node capacity. How are we going to verify that the feasibility of the cuts? So we guess the cuts, but we want to make sure that they're feasible. What do I mean by feasible cut? So this is how a cut looks in this setting. So we want to make sure that there is no edge between the two sides. Right? There is a separator, S, and then there are two sides, L and R. We want to make sure that this is a feasible cut, which means that there is no edge between any node in L to any node in R. Okay, so straightforwardly, we will just check every edge, and then we see, okay, from which part it is, and that's it. But that is too much. We want to do something that is faster than m time for every cut piece. Okay, so what we do is as follows. Consider the following matrix on which has q rows and n columns. There is a row for every pair of nodes in Q, and a column for every node in the graph, and there is one in an entry if the corresponding node belongs to the left side in the corresponding guess cut. So in this example, we have the row corresponding to the pair UV in Q, and then we look at the column corresponding to W, the node W. Now, W belongs to L, to the left side, so we put 1 in that entry. And otherwise, we just put 0. But this is the definition of the matrix.
Sorry, are you working with directed graphs, or
So
is this undirected max flow or directed?
yes, so the result itself, the framework itself, will work for everything. But for simplicity, I explain it on undirected graphs with unit node capacity.
So I'm just a little puzzled. Like, are these notion of left sets and right sets
It doesn't. It's just so that I can speak to you. Yeah.
Yeah, it's
Left is
easy.
L and R. Yeah. Just fix one and go with it. Okay. So this is the matrix, and And what we do is to simply multiply it with the incidence matrix of the graph. Okay, and then the observation is that the resulting matrix of that multiplication has 1 in entries corresponding to the columns of the right side, or it has at least 1 in those entries, if and only if there is an edge from the left side to those nodes. So that's something you should essentially just stare at it for a second, and you will see it. If you multiply these metrics as I defined with the incidence matrix of the graph, then you can identify whether there is an edge between the left side and the right side. Yeah, and the second thing would be to make sure that the values are correct. So that would be to just count the number of nodes in the separator and make sure that it is the same as what we guessed for. So that is how we make sure that the cut guesses are feasible. And now, as far as the flows, we don't do something that is faster for all of the pairs. We just verify that the flow that we guessed is feasible, so that there is the conservation of flow in every node, and that the capacities are being held. And also we want to make sure that the value is what we guessed. Okay, and that's it. That is essentially the framework. Is that clear? Okay. So now the second thing, as far as the techniques that I want to talk about, is the flow volume upper bound. So again, what it says is that in the node capacity graph, for every node pair U and V, there exists a maximum flow that doesn't use a lot of edges. It uses O of n edges. Maybe the existing algorithms would use many edges, but what I'm saying is that there's always a way to ship the maximum flow that doesn't use a lot of edges. And then the non-deterministic algorithm can just guess this flow. We just want to know that there exists a succinct way to ship the flow. Okay. So how are we going to show it? So this is a network, and let's say that and this is the maximum flow between S and T. Okay. And now, in general, this flow may contain cycles, right? Now there could be different kinds of cycles. So normal cycles, we can essentially assume, without loss of generality, that they do not exist, because we can just ship flow along them or against their direction, and then just cancel them. So in this instance, we would just decrease the flow along the cycle by 1, and thus we will eliminate the bottom edge, right? However, there could be other cycle in the underlying graph of the flow. Okay, so this is one example of that. This is not a cycle in the actual directed graph corresponding to the flow, but it is a cycle in the underlying graph. And so there could be different kinds of cycles, and those cycles can contribute a lot to the size that the flow requires. So the idea here is to eliminate what is called anti-directed cycles, or something that is close to it. So this is not something that that is trivial to assume that it doesn't exist. Nevertheless, it is possible to assume that it doesn't exist. Now, this is what I'm going to tell you a little bit about. So an anti-directed cycle essentially it's a cycle in the underlying graph that doesn't have a path of length 2. Or to put differently, the directions are interchangeably clockwise and counterclockwise. Okay? So now, if we take one of those cycles and we take the flow and we take the edge along the cycle that has a minimum amount of flow among all of the edges. Let's say this edge is E min. In this case, it is 3, the edge at the top. So we are going to cancel that edge by shipping flow along the cycle, right? So what we do, in other words, we cancel a flow of size f E min going counterclockwise, and we ship it clockwise instead, right? We ship flow along the cycle, in this case, clockwise. Now, what it does, the important thing to see here is that the total amount of flow along every node remains the same, right? So we're talking about node capacities, right? The capacities on the edges are essentially infinity. There's no bound on the capacities on the edges, but the bounds are only on the nodes. Now, when we do this operation in the analysis, the amount of flow on the nodes remains the same. Okay?
Am I missing something? Or in this way, you can cancel any undirected cycle regardless of what you have? What direction?
Any anti-directed cycle, yeah.
Okay, good.
Yeah, that's the idea. In the analysis, we want to assume that these cycles do not exist.
No, I don't mean just these good cycles where you have back force, but if you put arbitrary
Oh, no, that is not necessarily something that you can do.
Really?
Yeah, because imagine you have another kind of cycle that has a path of length 2. Then when you ship that extra flow through the middle node, it could surpass the capacity, the upper bound on the capacity on that node, right? So another way to say it, imagine that there is a node here.
Yeah.
Okay. Now, when you do this operation of shipping the flow clockwise, maybe you exceeded the upper bound that we have for that node when you do it.
Right, so let's take it offline.
Okay.
That's what is a little confusing for me too, because I mean, what goes into the node is the same flow that whatever the Texas flow that we're doing right now. In this case, it's 3 in the opposite direction, right? To cancel the flow on that.
Yeah.
But for every node, it's like 3 is the flow that's going in and 3 is the flow that's coming out, correct?
Or it could be that there is more than 3 in other nodes, right? So the flow can, let's say, come here and exit from here in many complicated ways. But now we are focusing only on the cycle, on what the flow does to a cycle, right? And then it could be different values. But the thing is that if we consider the minimum one among all of the edges, so the edge along the anti-directed cycle where the flow is minimal, then we're going to cancel that edge.
I understand that. I'm just saying that the net change, like right now, by this operation, the flow through the vertices don't change, right?
That's exactly the point, yes.
Yes. So I don't see, I mean, even as he was pointing out, if it's any underlying, like what is special about anti-directed cycles here? Because if I ship this flow like 3, for example, the directions don't matter, right? Like if I do this reverse 3, then still the net change of flow through any vertex here is still 0. So I don't see how this back-forth directions matter.
One of the constraints in maximum flow is the capacities, right? So in this case, there is an upper bound on the capacity on every node, right? So let's say that there was, again, an extra node here but the capacity was just 7, not more, right? In this case, you wouldn't be able to ship this extra flow on that node. But here, you can do it, right? Because the flow that is extra on every node also goes out of it. But if you had the path of length 2, then you wouldn't be able to say it on the middle node.
Okay, so I think maybe I probably am misunderstanding what node capacity is. So in my understanding, capacity of a node was like the maximum net flow through the node, like out minus.
There's a fixed number that nothing more than
What
that
is the
can be
definition
shipped
of-
on the node.
Right. When you say ship, like, can you define it mathematically? As in,
Yeah.
is it like outflow minus inflow, or max of like outflow?
So the inflow and the outflow are the same, but this is a number. Now this number has an upper bound, which is this upper bound that we're talking about, right? So for the flow to be feasible, the total amount of flow entering the node must be exactly the same as the flow exiting the node. That is an independent constraint of the upper bound of the capacity bound.
Here, we should take it offline because I'm not convinced also. Let's talk after.
Okay.
After the-
Right. Yeah.
I think you are right. Let's talk.
So after we ship that flow along the anti-directed cycle, this edge is cancelled, and then in the analysis we just do it over and over again until we can assume that no such anti-directed cycles, or the I'm going to be more precise in a second about the what we exactly are going to assume that doesn't exist in the flow. Okay, so how are we going to show that the flow without anti-directed cycles is succinct, is not too big? So what we do is we consider the bar parted graph. We just copy the nodes twice, and there is an edge from UL to VR if the edge existed in the graph. Okay? Now, let's say that there is a cycle in the underlying graph of this bipartite graph. That cycle implies that there is an anti-directed cycle in most cases. It implies that there is an anti-directed cycle in the given graph. So if there is no anti-directed cycle, if there are no anti-directed cycles in the graph, then this graph also doesn't have it. Now there is one case that I should talk a little bit about, is that this is not 100% correct. So it could be that there is a cycle in this underlying graph, but it goes through the same node, two copies of the same node in the right and the left side, and that corresponds to an anti-directed closed walk. So, and this is in fact the what we eliminate, what we assume that doesn't exist. Anti-directed closed walk, and exactly the same reasoning also holds here. Yeah. Okay. So so that was about the volume upper bound. Now I would like to tell you about the new randomized algorithm. Okay. So again, this is a new randomized Las Vegas algorithm for the setting of undirected graphs with unit node capacities. Now this algorithm is going to make around m applications of maximum flow and spend some additional time. Now, as I said, that's an independent improvement of existing algorithm to this problem. Okay, so essentially, what we do here is we're using an existing algorithm for edge capacities, and we try to make it work for node capacities. Now, there are going to be some obstacles, but this is in essence what I'm going to talk about, how we're going to overcome those obstacles. So first, I have to tell you about how this existing algorithm operates for edge capacities, undirected graphs in edge capacities. Okay. So one inequality that always holds in this setting of undirected graphs with edge capacities is that the maximum flow between every pair of nodes U and V is at least as high as the minimum between the max flow, the two other max flows. So we have kind of a triangle inequality here. For every three nodes W, U, and V, maximum flow between U and V is bigger, or at least as high as the minimum between the remaining two. Okay, now why this is correct? We can think of the minimum cut between U and V. W must belong to one of the sides, right? So let's say it belongs to the side of U. That means that this cut is a physical cut for the pair WV, but it could be that WV has an even better cut. Okay? So this is why this inequality holds. What it also means is that there could be at most two values among the three. There could not be three values, three different values. And also that the minimum value among them appears at least twice. Okay. So now, for sake of simplification, let's assume for a second that that we have a lot of distinct values. So what the algorithm does is it finds a pivot in some way, and then it finds the minimum cut from the pivot to all of the other nodes. And then this way, we are going to know something about all of the pairs, all of them, the maximum flow between all of the pairs. So now if we have this assumption that the maximum flow values from P to all of the other nodes are distinct, then it immediately tells us that we can get the maximum flow between every pair of nodes, and here is why. So let's say we have two nodes, U and V, and the maximum flow from P to U is smaller than the maximum flow from P to V. Now, what can we say about the maximum flow between U and V, given the inequality that I told you before? It must be the smaller among.
Oh, so here the important assumption is that they're all distinct.
Yes, yeah. Okay, and the reason is that again it follows from the inequality, but another way to see it is that when we look at the cut between P and U, again this is edge capacity, so it's just two parts. And then we ask, where is V? So it cannot be in the side of U, right? Because then it would mean that the cut is at least at most the size of the cut of U, but we know that it's bigger, right? We assume that the max flow from P to V is bigger than the max flow from P to U, right? So it must mean that V belongs to the side of P in that cut, right? And and that means that the maximum flow, that we have essentially the maximum flow from U to V, just given all of those cuts. Now, in the general case, this is not an assumption that we can make. Yeah.
So I kind of missed what P is like.
Sorry?
What is P here exactly? Like.
Yeah, P is a pivot that we pick, and then we find the maximum flow from P to all of the other nodes. Now, if we have this assumption that those values are distinct, then the point is that we can find the maximum flow between every pair of nodes, right? And the way to do it is to take the minimum one among the two values from P.
So far, we haven't addressed like how to find, like if there is there always such a pivot?
So I'm going to talk about it right now. Yeah, so in the general case, this is not an assumption that we can make, because it could be that P is such a node that there is just one cut, right? The cut between P and all of the other nodes is just the same cut, or there are not many cuts. But what we show in that paper was that if we pick a random pivot, then with constant probability, it is a good pivot. So there are many cuts, distinct cuts. And so the idea was to progress in a recursive manner, right? We find all of the cuts to all of the nodes. And then for every pair, if it belongs to separate cuts, then we know the value. And otherwise, then we continue forward in the recursion. Okay, so now, given those ideas, now we want to apply them to the node connectivity, to unit node capacities. So in high level, what we do is the same framework, and then we also want to apply reinforcement queries, so additional max flow queries when necessary. Now let's consider again. Let's apply the same framework and see what happens. So we take P, and then we have the maximum flows to all of the nodes, and let's say that they are distinctive. So now let's assume that the maximum flow to U is smaller than the maximum flow to V. Now we ask for the minimum one among them, the max flow between P and U. We ask where V could be. Now previously in the edge capacities, we concluded that it must be in the side of P. However, here it could also be in the separator, right? So we cannot conclude the same thing. However, this obstacle is not very bad, because what we can do is find the maximum flow between every node in the separator and the corresponding node in the other side. And because in this setting, the degree is an upper bound on the side of the separator, then the total extra amount of maximum flow calls is the sum of the degrees, which is M. Okay? But the second obstacle is a little more subtle. In this, the issue here is that the pivot itself might belong to the optimal separator. So we can imagine pairs UV where P itself belongs to the separator. Okay. So P must belong to the separator. However, by the design of our algorithms, of our algorithm here, all of the cuts from the pivot, in all of the cuts from the pivot, P belongs to one of the sides, right? It doesn't belong to the separator. So we wouldn't find this cut, and we wouldn't even know that this is not the optimal cut in our case. And the way that we overcome this obstacle is by the following observation. This issue is most significant when the separator is very big compared to the current instance. And in that case, a random pivot belongs to the separator with high probability, right? We want to say, so we pick a random pivot in order to have many distinct values, right? But the issue here is that if the separator is big, then there is a chance that a good chance that the pivot would belong to the separator. So this is the issue, and the solution is to compute the maximum flow between pairs of nodes with a very high degree in relation to the size of the instance. And then there is a way to show that this is post M additional maximum flow pairs.
Sorry, the solution is like you try to find a different pivot, or I'm confused. Like what is the solution?
Yeah. So we make additional extra reinforcement queries for pairs where this basic recursion doesn't find them well, right? So let's say we have a pair that is not good in a sense that there is a good chance that the pivot itself belongs to the separator, right? So the observation here is that this issue, in high level, this issue is most significant where the separator is big. Because if the separator is big compared to the side of the instance, then there is a good chance that the pivot would be in the separator, right? So we don't change the basic recursion, we just do extra maximum flow queries.
For those pairs.
Yeah, what do we know about them? So if the separator of the maximum flow is big, it also means that the degree is big, right? And there aren't many nodes with high degree.
And so you just want to compute max flow directly between
Yes,
those nodes.
yes. Yeah.
hopefully you don't have too many such nodes.
Yes, exactly. Yeah. And the last part focuses on converting to Las Vegas, right? So this algorithm makes errors if still P belongs to the. There is a good probability that it doesn't happen, but it could still happen, and we want something that is that has no errors. Okay, so the idea of the solution here is to repeat roughly k times. Okay, to repeat the algorithm k times, and then we can conclude that at least k different pivots will be chosen, and so one of them will be outside of the separator. So we can verify that k different pivots are chosen, and then we can conclude that at least one of them would be out of the separator. If we're focusing on pairs where the maximum flow is bounded by k, right? So we repeat k times, and then we're good for those that are closed roughly k.
This is like a guarantee, like without any error. That's what you're saying.
Yeah. So it could take a lot of time, but no error, right? This Las Vegas versus Monte Carlo. Yeah. So we repeat, and we make sure that there are many pivots. Now, because we repeat k times, the total number of reinforcement queries is mk, right? It's not m. We want just m. So this is the actual solution. We solve in buckets. So each stage focuses on maximum flow values that are between k and 2k. And that means that the number of terminals is for a stage of k is m over k, because that's the amount of nodes whose flow are at least k, all right, the bound of the degree. And then for each one of those, we repeat roughly k times. This ensures that the total number of pivots chosen in this stage is big enough, so that at least one would be outside of the separator. Now that decreases the number of terminals to m over k, but again, the number of maximum flow calls can still be high, mk, and the way to handle that is to only make the maximum flow call if it is required k times. So we have k repetitions. If a certain pair was required k times by this logic that I described, only then we make the maximum flow. And the idea is that if it happened, then we're good. We have made the query directly. If it didn't, it means that the basic recursion separated the pair many times. And again, in particular, in one of those times, the pivot was outside of the separator. So it's kind of a win-win situation. Now, I want to end with the following open problems. Either break the n to the fourth time for any of the hard variant, or to improve the unit edge capacity to m squared, just like we showed here on the unit node capacities. But maybe the most important one is to find a non-deterministic algorithm, or to say anything essentially about directed graphs with edge capacities, which is the most difficult setting.